Murphy. Nice to meet you.
Good to meet you. Will I share my screen?
Yes, my pleasure to meet you. I'm going to host the next session. So I think I can start now, right? Are you ready?
Yes, will I share my screen?
Oh, no, I will just give a very brief introduction of you first. Okay, just a very short welcome speech. Okay, so I guess this is a good evening in China, maybe a good afternoon or good morning in the at the European side.
Good morning.
Hi, welcome to today's CUE meeting. And I'm Joshua from Shandong University, China, and I'm going to host for the session. So now it's my honor to briefly introduce our keynote speaker for the for the current session. So now I'm going to simply just read the Professor Murphy's CV. So Professor Jerry Murphy is the director of the Marine Center for Energy, Climate and Marine with C.220 researchers. He has published over 119 peer-reviewed journal papers. He was awarded the Engineers Ireland Excellence Award for Best Paper, Excellency in Marine Research, adjunct professor at the University of Southern Queensland in 2018, and was elected to international membership of the Science Advisory Board of DBFZ in 2019. He was elected by his peers as the leader of the International Energy Agency Bioenergy Task, Energy from Biogas, for the trimester 2016 to 2018, and re-elected unanimously for the period 2019 to 2021. And today, Professor Murphy's title for the topic is Use of the Power of the Ocean to Decarbonize the Society in Circular Economy, Energy, and Environmental Systems. So now I will give the conference room to you. I give the microphone to you, Mr. Murphy. Are you ready? So now you can share the screen. Yeah.
Let's talk to. This is the hard bit, getting the technology to work. It's the piece I worry about.
No worries. Take your time. Oh, I can see it clearly.
Okay. I'll maximize. You might just let me know if the slide is showing for you. Can you see my slide?
Yes, very clear. Yes.
Thank you very much. So I will start.
Yes, please.
So I'd like to present on the power and the resource of the ocean as a means of decarbonizing society and circular economy, energy and environmental systems. And this work is the work of my good colleagues, Professor Richard Lin in Southeastern University, Davy Wall, Richie O'Shea, Chen Den, Ben Ten Wu, and Arkisman Bosey. So this reflects the work of our research team. I've been introduced. Thank you for that introduction. MARI, I've been the director of for 8 years, and it's a national center where we look at energy, climate, and marine. And I suppose the work I'm concentrating on today is renewable fuels, offshore renewables, and a bit of climate mitigation. MARI has, at the moment, 250 researchers, and we do a lot of work with industry. We've had 103 industries where we've co-designed solutions to decarbonization problems. And as a center, we brought in about 60 million euros for projects. And these are the people. So it's always about the intellectual abilities and what's inside the brains of our researchers. So these are some of our researchers at our last gathering. The work I'm going to talk about is the work of these brilliant colleagues of mine, Dr. Arkisman Bosey, Davy Wall, Richie O'Shea, and Richard Ling has just left us for a full chair at the Southeastern University. So I'll reflect the work of these people. It's always a collaborative process. this is our canvas. This is sort of where we take our inspiration, and there might be a lot in this, but I hope to go through the presentation and outline the areas of work that we feel are important to decarbonize society. I suppose one of the things we look at is the grand challenges of decarbonizing transport, industry, and agriculture. So we look at these as grand challenges, and I suppose we take for granted that there will be electric cars, there will be renewable electricity, but we're trying to look at the difficult pieces. And I suppose a lot of what we look at is zero carbon. And as an engineer, as a mathematical engineer, I find zero very difficult. And whenever we look at things, we find it very, very difficult to get to zero. We can see large swathes of decarbonization, but zero always is difficult. And as you get closer to zero, it gets more expensive, it gets more murky, it gets a little bit dirtier. So we look at difficult aspects of the decarbonization. So typically we start with renewable energy, and we're very lucky in our center. We are the National Ocean Test Facility. We have 4 large wave tanks. We can test devices at 1:10. So a 1 meter wave becomes a 10 meter wave. And we've tested lots of floating offshore wind devices and oscillating wave columns. We have circular tanks where waves can come in different directions, and we can measure at 1/100 of a second the movement of the devices in our facilities. So lots of different devices are tested, and it gives us lots of data. We can also put wind down these tanks to look at the effect of currents, of winds, of waves. And this work is led by Jimmy Murphy, my good colleague. So we sort of use that data to look at how does that energy best used for society as a whole. And one of the areas obviously is hydrogen. So the perspective we have is that Ireland is an island. If you're familiar with the geography, we have about 3,000 kilometers of coast. We have a population of about 6 million people. We sit off the northwest coast of Europe. Britain is between us and the mainland of Europe. But we have a huge resource of ocean. In terms of actual land under our authority, we're the biggest country in Europe. We've got this massive amount of ocean that is in our area. And the perspective we have is that we will keep building offshore wind until we satisfy electrical demand at the lowest level of capacity factor. So for example, if Ireland has a requirement for 8 gigawatts of electricity, we're a small country. If we build 60 gigawatts, that will at all times cover the requirement for a country, even when it's not that windy. And the idea is that the rest of the electricity could be converted to hydrogen. So we're looking at a sort of a hybrid model. Initially, we manage electricity, but afterwards we look at other things. And what's quite important is that gas, and we've seen a problem in Europe at the moment with the lack of gas from Russia coming into Europe. Europe and the US uses twice as much energy from the gas grid as the electricity grid. So gas as an energy vector is very, very important. And we visited facilities such as glass plants. In the production of glass, you have to have gas. There's no other way. You need a gas. So gas is very, very important. Ireland has about 8 gigawatts of electrical capacity at the moment, and that's 40% of our electricity is covered by wind. An issue for Ireland is we are an island. We are an island, so we have an islanded grid. We're not well connected with other countries. And we've experienced the highest levels of system non-synchronous penetration of any electrical grid. We've gone to 75%, meaning at any one time, 75% of the electricity is coming from a variable renewable source, which is wind generation. We've just spent 150 million on a flywheel in Ireland that will cover inertia problems. Now, I'm not an electrical engineer, but this is very challenging. full electrification is very, very challenging. And Ireland has a target of 7 gigawatts of offshore wind by 2030. We have a target of 2 gigawatts of hydrogen, and we've signed the Dublin Declaration with our neighbours that in the northern seas of Europe, there'll be 260 gigawatts of offshore wind. And this is quite challenging. One reason it's challenging is we've just signed a contract with France for a 700 megawatt HVDC cable to have some connection with France. And that's about €1 billion. So we're looking at very large HVDC cables coming ashore. And my understanding is the maximum size is 1 gigawatt. So we have a very challenging logistical problem in managing offshore wind to the level that we want. If we look at curtailment and constraint, Ireland is an island, and we have about 5.5 gigawatts of wind, and that corresponds to 12% dispatch down. So we have to spill electricity either due to constraint or curtailment. So not all our electricity is actually used because it's produced when, for example, a summer night, we're all in bed, it's windy, loads of electricity, and we don't use it. So we've started looking at hydrogen as a way of capturing that electricity that isn't used. And one of the things we looked at is if we had electrolyzers just for the curtailed electricity, just for 2 or 3 hours at nighttime. So what would happen is we would be running, if you follow the red line, about 3,000 hours a year. The bid price would be about 4 cents a kilowatt hour, but the levelized cost of energy would be €200 a megawatt hour. However, if we ran for 6,000 hours a year, that would correspond to a bid price of about 6 cents a kilowatt hour, and our levelized cost of energy would be €100 a megawatt hour. So we need to sweat the assets. If we buy electrolyzers, they can't hang around for a few hours when we're curtailing electricity. They need to be operating a lot of the time. And €100 a megawatt hour is €3 a kilogram of hydrogen, is about €1 per litre of diesel displaced. So we're looking at this idea of offshore wind farms. And should they produce electricity? Should they produce hydrogen, or both? So one of our papers looked at, we would sell electricity until the demand fell. And when the demand falls, we're satisfying the country's electrical demand and electricity becomes cheap. So we looked at, through a model, roughly 4 cents a kilowatt hour is the crossover. So we now produce hydrogen. And that would give a levelized cost of hydrogen of €3.77 a kilogram, which is 11 cents a kilowatt hour. So if we have electricity at 4 cents a kilowatt hour, we produce hydrogen at 11 cents a kilowatt hour. And there is conversations about storing hydrogen for 20 days underground so that we can manage those winter periods when it's very cold and there's no wind. But if we go from hydrogen back to electricity at 60% electrical efficiency, that's 18 cents a kilowatt hour. So there is a challenge in that electricity produced at 4 cents a kilowatt hour, when you go to hydrogen and back to electricity, will be 18 cents a kilowatt hour. And that's the base cost. There'll be more transmission costs on top of that. However, our utilities are looking at hydrogen as a means of dealing with peak electricity. However, if we look at transport fuel, that hydrogen is 11 cents a kilowatt hour, is 113 per litre of diesel. And furthermore, if we put it into a fuel cell, which is a higher efficiency of an internal combustion engine, it's about 90 cents per litre of diesel equivalent. So our perspective is hydrogen from offshore wind is very, very viable for transport. We've also looked at, where do we put these electrolyzers? Are they on land? Are they on sea? Are they on every wind turbine? Is there a platform where the turbines connect to? Now, in the future, we're looking at 20 megawatt wind turbines. They're 500 meters high. And one of our projects is looking at a 20 megawatt electrolyzer, a battery, which is also required, a desalination unit because we need water, and an electrolyzer. So we're looking at a massive factory 65 kilometers out in the ocean. We're looking at Brinny discharge, which brings in the whole area of of the habitat and what will happen. But the joy of producing hydrogen offshore is that you can get a lot of power through a hydrogen pipe, where the HVDC cable is really limited to a gigawatt. So there are advantages and disadvantages of where the hydrogen is made. I want to look at anaerobic digestion because this is very much part of the circular economy system. I served for 6 years as the leader of the International Energy Agency, TCP, in bioenergy, and we produced 14 or 15 reports and 20 or 30 case stories. But anaerobic digestion, in my perspective, is the epitome of the circular economy system. It deals with food waste, with slurries. It can produce a transport fuel, combined heat and power. It reduces fugitive emissions from open slurry tanks. And for example, we looked at an organic farm, and this farm is in Denmark. And when you go organic, you've no chemical fertilizer, no weed killer, and the yields of your crops decrease. So the biogas plant was built as a means of having a organic biofertilizer. So all of their dungs went to the digester, they were liquefied, the minerals were far more available. So we made a fertilizer from dung that was better than dung. The yields went back up, and now the milk is assessed as greenhouse gas negative. So again, we would see anaerobic digestion being essential for organic farms. One of our partners in Brazil had 400 hectares of grassland, and it was a nuisance what to do with the grass. Finally, they're now running 60 cars off that parkland grass. And then we looked at Denmark, which has really gone for scale. And one of the things they did in Denmark is back in 2010, they told farmers by 2030, you can't spread slurry on the land raw. They had problems with eutrophication. They had problem with wells. So the government funded the farmers to have 6 months storage, and the farmers co-opt, so very, very large digesters with a catchment of up to 20 kilometers. So a farmer can take his or her dung to a pit, it's augured to the digester has an anchor tenant, which could be the food waste from a city, it could be the byproducts of a dairy industry. So all of these facilities happen at the digester, and then the digestate is augured back out to the farmer who's got a biofertilizer. We're also looking at this sort of multiple products from a digester. In Denmark, there is one biogas facility that puts the methane in the gas grid, and the CO2 is scrubbed to be food scale or food level CO2. And in Denmark, the demand for CO2 in hospitals, in laboratories, in the food industry is 65,000 tons. And a quarter of this is met by one large digester. So again, we have products such as CO2, we have biofertilizer, and we have the biogas. What's quite important is that the open slurry tanks that we have all over our countries emit methane to the atmosphere. So if you have an open slurry tank, typically 17.5% goes up to the atmosphere at a global warming potential of 28. If you cover that tank and make it an anaerobic digester, you can limit slippage to 2%. So there's a reduction in 15% of methane that's going up to the gas grid. And in our report, we looked at if we had 2% losses on a whole life cycle basis, we would be at minus 250 grams CO2 per megajoule. And this corresponds with the California Air Resources Board, who awarded a carbon intensity of minus 255 grams CO2 per megajoule. So covering slurry pits and using the methane captured to power buses, which then emit CO2, which is 28 times lower global warming potential than methane, is a good thing. So we're in this circular economy, energy, environmental type system. And we also looked at biogas as a means of working in a co-op. So this is in Switzerland, where a co-op has hydroelectric scheme, a wind turbine, and they have biogas, and they sell electricity as a unit. But the biogas allows them to be flexible. So by night, they use biogas. Excuse me. When the wind isn't blowing, they use biogas. So biogas allows them to match the profile of which they sell their market or their electricity in the market. I now want to move up to biological methanation. So we've looked at hydrogen, and one of the things we're very interested in is power to X. So we're interested in the hydrogen molecule rather than hydrogen gas, which is very, very, very voluminous. So we want to look at pathways to go from hydrogen to methane to methanol to Fischer-Tropsch diesel. So we do see hydrogen as being a very, very important molecule. And one of the first steps is to methane. So we visited the north of Germany, Wurtel, and Audi built a facility next to an anaerobic digester, which was treating food waste. And the methane goes to the gas grid and the CO2 is left behind. So we can capture that CO2. And they built an electrolyzer of 6 megawatts. And they tell us they don't pay for electricity. What happens is when there is too much electricity, rather than asking a producer to go offline, they spill the electricity to this electrolyzer. So the hydrogen in the electrolyzer is reacted with the carbon dioxide from the food waste to make synthetic methane. So we talk about the Sabatier equation. 4 moles of hydrogen, 1 mole of CO2 gives us methane and water. So the hydrogen from wind is reacted with CO2, which is a byproduct from the digester, to make methane. And it's used to power 1,000 Audi natural gas vehicles. It's a catalytic process. It operates at around 400 degrees Celsius, and there's a certain sensitivity. So as a biological engineer, we started looking at anaerobic digestion, and anaerobic digestion has complex polymers which are hydrolyzed to monomers, which are fermented to acids, which are then brought down to these acetogenic bacteria, which produce hydrogen and CO2. And then we've methanogenic RK here. 4.1 uses hydrogen and carbon dioxide to make methane and water. So we can see 2H2 plus 0.5 CO2 is methane and water, and it's a very exothermic reaction. It's a lovely reaction. It will happen. So rather than having a catalytic process, we could have a biological process. So we added hydrogen and carbon dioxide to a batch of anaerobic broth, and we fed it over time, and all they got was hydrogen and carbon dioxide. There was no food, no substrates. And we found Methanothermobacter wolffi became dominant. And the reaction here is 4H2 plus CO2 is methane and water. The performance was up about 95%, and we looked at mesophilic and thermophilic, but it worked, and it worked quite readily. So then we started doing more things. We built a reactor, and we started operating it in different ways. So number one, we looked at in situ. So if you put hydrogen into an anaerobic reactor, you're still going to have CO2. So that wasn't very successful. So our in situ system down here, we were getting maybe 70% methane. We then looked at an ex situ. So ex situ is very much this. There's nothing else happening. We're only feeding hydrogen and carbon dioxide to the bugs. And we found we were up at 95%. But then we looked at a continuous process. So as you tax the system, so this is a continuous ex situ, and we're getting 80% efficiency. But as the rate went up, it dropped off. And then when we added methane to the mix, so rather than just hydrogen and carbon dioxide, if we had hydrogen, carbon dioxide, and methane, then the efficiency was lower because the partial pressures were upset. So we came up with this idea of a sequencing backed system. So hydrogen and carbon dioxide or methane goes into a reactor. The hydrogen is recirculated because it doesn't go into solution readily. And then it goes to a second reactor, and then it goes to a third reactor. So what we did is we found these compositions of gas, and we used one of our reactors, and we modeled this approach. So we could get a very, very good conversion in a continuous mode. And then we built this. So this is R1, R2, R3, based on R1, R2, R3. And we ran this system, and we found this is R1, the first reactor, R2 is the second reactor, R3 is the third reactor. We were getting 97% conversion to methane in a continuous system at a short retention time. So we're very, very happy. Now, these results are as yet not published. So then now we're looking at, we've looked at hydrogen from offshore wind, and we can convert it to methane biologically, or the Sabatier process as used by Audi. But we wanted to tie it together with anaerobic digestion. So we visited a facility in Denmark, and we published this within the IEA Bioenergy. They put an electrolyzer in a wastewater treatment plant. There was already a digester there, and the digester was getting 125 meters cubed of biogas, of which 50 was CO2. So at this biocat process, they added 4 times the CO2 as hydrogen, 200 meters cubed of hydrogen, which required a megawatt of electrical power, but all that CO2 became methane. So you now have your 75 meters cubed of biomethane, but you have 50 meters cubed of synthetic biomethane. And what this has done, it's upgraded the biogas. So we're replacing traditional biogas upgrading with an electrolyzer. We're passing methane, carbon dioxide, and hydrogen through a system, and out the other side, we're getting methane and only methane. So we've increased our output by about 67%. So this is working. We then looked at that there are 12,000 anaerobic digesters in Germany alone. If every anaerobic digester put an electrolyzer next to it and had an ex situ biomethanation system, we could increase the output of all those digesters by 67%. In Denmark, at the moment, they have very large anaerobic digesters, and we work a little bit with Nature Energy, Ole Helvepund. In Denmark, at the moment, 25% of natural gas is coming from biomethane on average over the year. In the summer, they probably have a lot more, in the winter, somewhat less. But there's a target for 2035 to replace all natural gas with biomethane. And what would help in this is placing electrolyzers and ex situ biomethanation at every anaerobic digestion system, so they can see a very large resource. So it's viable combining anaerobic digestion with power to X that we can replace natural gas in the gas grid. We looked at a situation in Ireland. So I live in a city, Cork, and planning can be quite difficult. We have a wastewater treatment plant for 426,000 PE. So we thought, how about putting the electrolyzer at the wastewater treatment plant, where there won't be many issues, we hope, because very few people go to the wastewater treatment plant. And we looked at supplying the oxygen demand. So rather than pumping air, we would pump oxygen, and the oxygen would come from the electrolyzer, which in essence is reducing the pumping by a factor of 5. So we're decarbonizing the wastewater treatment plant. The electricity that comes from offshore wind would go to a 10 megawatt electrolyzer, which would cover the oxygen demand. But the hydrogen then could go to the existing anaerobic reactors to upgrade the biogas to pure methane for trucks. And we found that only a third of the hydrogen was required. 70% was available to do whatever we wanted to do with hydrogen. So we published this in Advances in Applied Energy, and we found we could power 400 heavy goods vehicles, decarbonize the wastewater treatment plant, and we captured the curtailed electricity from 18 8-megawatt turbines. So it was a nice bespoke application for our own city. We then wanted to look back at anaerobic digestion and to get a bit more detailed in how this works. So again, if we look at the flow chart, one of the things in the anaerobic digestion process is that the acetogenic bacteria, if we break down ethanol by acetogenic bacteria to acetate and hydrogen, the standard free energy is positive, which means it's not likely to occur. So this reaction from the acetogenic bacteria only works in the presence of the hydrogenotrophic methanogenic archaea. So we're back to our guy here who converts hydrogen and carbon dioxide to methane and water, which is very, very favorable. So there's a syntropic mutualism between this bacteria and this archaea. So what we started looking at is, how do we make this reaction better? So we have this mediated interspecies electron transfer, which is this reaction. And what we proposed was a direct interspecies electron transfer. So if we got conductive material and formed a little electron bridge. So by adding conductive material, we could have hydrogen ions popping across and make the reaction more favorable. So this is a paper we published in the Chemical Engineering Journal, where we looked at mediated interspecies electron transfer with a positive standard free energy. But when we added graphene, we could form this electron bridge. The reaction occurred a lot faster, and we can see that the standard free energy is minus 150. We looked then at a stillage reactor that was under stress. It wasn't working well. And when we added graphene, it stabilized the whole system. So we're seeing the benefit of adding conductive material. However, graphene is very, very expensive. It's seen as a wonderful element that does great things. So we started looking at pyrochar. So we introduced the concept of pyrolysis. And this was quite serendipitous because we're doing a lot of work with the brewing industry and the distilling industry. And we're looking at really large distilleries requiring really large digesters, requiring massive land spread areas for the digestate. So if we separated digestate into solid and liquid and pyrolyze the solid element, we would get more gas, we would get pyro oil, but we'd also get pyrochar or biochar. So we're now looking at this type of system where we have organic substrates being pre-treated into an anaerobic reactor. We have power to gas giving us hydrogen to upgrade the biogas. We're taking our digestate to pyrolysis. We're making a pyrochar, and that pyrochar can go back into the anaerobic reactor to make it work better, to stabilize it, to increase the production of methane. And the pyrochar would eventually go back to land. It's almost pure carbon, so it's a soil organic content enhancer, which is deemed a negative emission technology. So we would be reducing the greenhouse gas in the agricultural process by increasing the carbon in the soil and increasing photosynthesis. So we started looking at pyrochar, and what we found was there's very different data in the literature. Some people say it works, some people say it doesn't work, but it depends on what the pyrochar is made for. Is it from wood? Is it from a draft? Is it from straw? Is it from digestate? What temperature is it made? So we do a lot of work with the distilleries in Ireland and in Europe. So we looked at draft, and draft is a solid byproduct from producing whiskey, and we heated it to various temperature ranges, but we found 700 degrees Celsius gave us the best results. And the graphite carbon, the oxygen, and the N functional groups were very, very important in this process. So then we went back to the ocean. Cork is a coastal city. We have lots of beaches, we have lots of seaweed, and there's been lots of conversations about seaweed as a source of biorefinery and biofuels. So we looked here at Laminara digitata, where I live. This is only 500 meters from where I live. That's where I get my laminaria. We brought it in January, February, March, April, May, June, July, and we looked at the carbohydrate content and the protein content and the salt content. And we found the seaweed ripens around August, September. And the carbon to nitrogen ratio looked good in August at 32. And when we did biomethane potential assays, we found August gave us the best results, around 53 meters cubed of methane per ton of Laminara digitata. But we never got the theoretical methane production. There was always an inefficiency. It was also difficult because there's a lot of salt in seaweed, and the carbohydrates are different. We have arabinose. So if you have a digester that's used to food waste or slurry, and you feed it seaweed with salt and arabinose, it's difficult. But we did look at anaerobic digestion of Laminara digitata and Saccharina lactissima, which is a sugar kelp and a common kelp. And we looked at the idea of feeding the digester, adding pyrochar into the anaerobic digester, and we compared it with graphene. So we know graphene works very, very well, but it's expensive. So graphene increased the yield of methane by 24% for Laminara digitata. Biochar did 17%. So we were getting something almost as good as the graphene, but it was a lot cheaper. So it sort of reinforced our idea of this circular economy of digesting byproducts and pyrolyzing those byproducts to make a pyrochar. If we go back to seaweed, one of the things we found with seaweed was our anaerobic bugs weren't all that happy, and it took them a long time. So we looked at a two-phase system. We looked at a hydrolytic reactor at a pH of about 5, a 4-day retention time, very high organic loading rate to make volatile fatty acids. And then those volatile fatty acids, such as acetic acid and butyric acid, would be fed to a methanation reactor. And those guys would be very, very happy because they're very used to acetic acid. This guy down here, M3, got the seaweed as is, 24-day retention time. And what we found interesting is that this monodigestion of seaweed in the single reactor gave us 7.9 megajoules of gas per kilogram of volatile solid at a 24-day retention time. However, if we look at H1 and M2, it was a combined 16-day retention time, and we got more energy because the methanogens were very happy with the volatile fatty acids. We also found we could make lovely volatile fatty acids. So rather than going to biogas, we could make volatile fatty acids, hydrogen, ethanol, which would have higher economic value. So what we looked at then was, if we had only this reactor, the hydrolysis reactor, and we added pyrochar in that reactor, we could push the reaction over here. This red guy is laminaria digitati and wood biochar. This black is the control. So we could increase the rate of production of the volatile fatty acids, and almost half the reactor required and the retention time to make our volatile fatty acids. So now we're wanting to look at pyrolysis and biological methanation. So when we looked at biological methanation, when we added hydrogen and carbon dioxide to reactors to make methane and water, it works quite well, as we have seen. However, when the system is turned on and turned off and turned on and turned off, and it's intermittent, which we would expect with depending on surplus electricity, what we found was it became unstable, it became unsettled, and by adding graphene, we were able to recover the conversion efficiency, and the process worked better. So this brought us to the idea of this whole integrated system of food waste and slurries and seaweeds going into an anaerobic reactor, producing digestate. The digestate is pyrolyzed for syngas and bio-oil and pyrochar. Our offshore wind goes to power to gas. We produce hydrogen. Oxygen is used, hopefully, maybe in a wastewater treatment plant. The hydrogen reacts with the biogas to give us pure methane. And if this is intermittent, our pyrochar will make the biomethanation more stable. And then the pyrochar goes back onto land as a negative emission technology. So we see lots of little loops in the system, which are all good for decarbonization. We then started looking at other ways to upgrade biogas. And we started looking at microalgae. And we're looking at photosynthetic biogas upgrading. So our biogas from the anaerobic digestion would go into a column, a carbonate bicarbonate cycle, and the CO2 would become bicarbonate, but we would also have microalgae going up that reactor, and they would use the bicarbonate for production. And the microalgae would convert the bicarbonate to carbonate, which goes back into the tower. So in essence, our biogas is going up the tower, our microalgae is going up the tower, we're producing microalgae. And that microalgae can be used for many, many things. I've been in China before with my colleagues in Zhejiang, and they were selling compressed microalgae as a food supplement at high value. So it's a vegan food. So we're now looking at producing biogas, biofertilizer, and food. An issue we have with policymakers is they're not technologists. So the Irish government had a climate action plan, and they looked at the marginal abatement cost curve. And this is used, I think it's developed by McKinsey. It's used across the world to decide what is the best spending of money per ton of carbon. So for example, down here, if you're beneath the line, if you're negative, it means it's really good. A negative marginal abatement cost means you're making money by doing this decarbonization. So switching from internal combustion engine delivery vans to BEV was seen as really, really good. The width of the line is the resource. Now, if you go out across this line, you'll find an orange box. and the marginal abatement cost curve was over 300 euros a ton, and it's agricultural biomethane. So we were very depressed, and we were not happy with this result, because there's so many applications of anaerobic digestion for the government to say the marginal abatement cost curve of biogas is above the line, it's 350 euros a ton, and we're not doing it because we have plenty other resources. So if we go back to our microalgae producing biomethane, food and biofertilizer, now there's many scenarios. There's digesting different feedstocks and producing microalgae, but we found we could be negative, selling microalgae as a vegan food to displace beef, to displace fish, to displace tofu. And we have all these different scenarios of a negative marginal abatement cost curve. So we are talking to our government saying, look, that curve you have is really not learned. It's a two-dimensional thing. It doesn't understand the intricacies of a biorefinery, bioenergy, biomethane production system. We then started looking at microbial electrolysis cells. So if you have an anaerobic reactor and you put electrodes into that reactor with maybe 1 volt currency, at the biocathode, CO2 converts to methane. So it's almost like an upgrading system. Again, this is as of yet unpublished. If we put a 1 electron current into a biocathode, we get 6 times the energy back as the electricity that went in. So the electricity is a catalyst. It causes reactions to occur. It converts CO2 to methane. So by putting the electrode in and putting electricity in, we get 6 times the return of the electricity that went in. So we have this system of upgrading, microalgae, biorefinery, biochar. So our system is varied, and we offer solutions rather than definitive pathways. We then started looking at industry and haulage and how could all this be used for the benefit of society. We looked at a distillery which is very nearby, and we found that there are many ways to decarbonize, but we found the best solution was number 20, which included for anaerobic digestion. But we're working now with 9 distilleries across the planet. But we found in the largest distillery, we could have cheap decarbonization, but we couldn't get beyond 67% unless we had digestion of the byproducts. And with reference to the last presentation, biogas can be used in scope 3 in bringing trucks into the distillery. The digestate from the biogas can be used as scope 3 as a fertilizer for the grain that makes the whiskey, or the biogas can be used in scope 1 by replacing the natural gas on the system. What we then started looking at was steel, ammonia, and methanol. Within the IEA, the perspective is we need to get rid of hydrogen. Hydrogen comes from natural gas. In Europe, our hydrogen comes from Russian natural gas that's steam methane reformed, and that is used to produce ammonia. It's used to produce a methanol. And in the full decarbonization of planet Earth, we need decarbonized ammonia and decarbonized methanol. And we also need to look at steel. The steel we use for the offshore wind has a carbon footprint, and we can use hydrogen to make green steel. So we found going from biogas to methanol was very easy. So we have CH4 is biogas, CH3OH is methanol. So we can go from biogas to methanol in a process, but we won't get full conversion because of the stoichiometric ratios. We need to bring in hydrogen from an electrolyzer. We can reform the methane to carbon monoxide, and carbon monoxide and hydrogen gives us methanol. So methanol is a very easy step from methane. And we found we could go to Fischer-Tropsch diesel, and we looked at the energy balances, and we found that if the electricity is surplus, we can get a 4-fold return in the first one here is methane, this is methanol, this is Fischer-Tropsch. However, if it's from offshore wind and the primary energy factor is 1, we're getting a 9% return or a 25% return or a 10% return. So it's not that good. But again, we have published in Advances in Applied Energy, and we looked at ships, trucks, and planes. This is the nadir. You're heavy and you require lots of space. And this is where lithium-ion battery sits. You're not going to have a battery plane taking you to Dubai from London. This is the utopian point, and no one's in utopia. But we looked at jet fuel. And the best fuels would be methanol to gasoline or Fischer-Tropsch diesel. So even though these have a bad energy balance, it's probably the only way of flying planes and ships. We need these electrofuels. We look then at trucks, and this is published in Advances in Applied Energy, and we looked at trucks running on electricity below 450 kilometers, and the marginal abatement cost was really, really good, depending on the source of electricity. Beyond 450 kilometers, we needed hydrogen fuel cells, but we found that the power to liquids did not work. They were too expensive. What we also found of interest is the electricity used by one truck, a BEV, is 185 megawatt hours, but for a fuel cell is roughly 500. So a battery is best. Hydrogen is next best. And beyond that, for shipping, for trucks, for boats, we then need methanol and we need ammonia. In one of our present papers that we're working on, we reckon ammonia is the best choice. We're looking at a ship coming from Shanghai to Rotterdam. We're looking at the total cost of ownership, but methanol seems to be the way forward. And the perspectives of our colleagues in the marine industry is they won't do ammonia, because if there's a crash, ammonia will form a fog, an asphyxiant that will kill the sailors. So you have to look at fuels under different perspectives in terms of carbon, in terms of cost, in terms of health and safety. So methanol will be the shipping fuel that will decarbonize shipping. And we reckon we need a drop-in fuel for planes. So this is a concept that I have borrowed from my colleagues in Germany. They have this idea of offshore wind in the North Sea, big electrolyzers. The oxygen goes to the cement factory to make a lean cement. We capture the CO2 from the cement factory. We react it with the hydrogen to make methanol. Methanol is converted to synthetic kerosene, and we have aviation. So we're now looking at this circular economy system: offshore wind, electrolyzers, district heating, green cement, and sustainable aviation fuel. So there's many, many ways of doing this. So again, this is our canvas. This is what we work in. And we're looking at the hard to abate sectors. One thing we're working at the moment, it's not published, but we're working at renewable fertilizer NH3 from offshore wind in the Haber-Bosch process. And we can obviously decarbonize the production of fertilizer. But when fertilizer is put on the land, there will be nitrosomus and nitrobacter, and they will make N2O. So even by decarbonizing the production of fertilizer, there will still be emissions from fertilizer on the land. So I suppose my synopsis is there's lots of things we can do, but getting to zero carbon is very, 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 very challenging. And a lot of my colleagues consider me a carbon junkie, that I'm always looking at carbon rather than electrification. I'm a huge fan of electrification. I have PD in my house, I have an electric car, but to get to zero carbon, we're going to have to go to ammonia, methanol, power to X, anaerobic digestion. We're going to have to treat our waste. We're going to have to look at circular economy systems. I think that's my presentation done. Thank you very much for listening to me.
Well, thank you, Professor Murphy. That's a very interesting and comprehensive introduction of your group's research. I think there is a lot of new knowledge I've learned, and I think the audience also needs to take some time to absorb. Okay, so now we come to the Q&A section. Any questions from the audience? Okay, I guess I can use my privilege as a host, so I can ask several questions first. Since I'm not an expert in these technologies, I would just ask very broad questions. So, Professor, have you ever estimated if all these technologies you introduced can be applied to, for example, to Ireland? Have you ever estimated that how much greenhouse gas emissions can be reduced?
I suppose what we provide is a menu of options, and we're slow to be definite. We're very slow to say this is the solution, because we do find that it depends on air quality, it depends on environmental, it depends on cost, it depends on greenhouse gas savings. But one of the things we are looking at is off the west coast of Ireland, we have a huge resource of ocean. We reckon we're going to put 70 gigawatts of offshore wind off the west coast of Ireland. And we do have cement factories and other sources of CO2. So the idea is to take out the cement factory, or sorry, my apologies. We do have a coal power burning plant adjacent to a cement factory. So the idea is take out the coal power burning plant and replace it with an electrolyzer, which will have a gigawatt of infrastructure around it. So we can have up to a gigawatt of hydrogen production, and we will capture the CO2 from the cement factory. And we're looking at that because our biggest airport is adjacent to this place in the west of Ireland, it's Shannon Airport. And we have a very large leasing fleet there. So we're looking at the idea of offshore wind, capture CO2 from cement, produce a methanol, produce a sustainable aviation fuel, which can be piloted at an airport, which is adjacent. And we do talk about hydrogen valleys. And we do think everything is bespoke. I mean, what would work in a hydrogen valley in the west of Ireland will be different than in Zhejiang or Chongqing. Like, you need to look at your cities, and I've been to Chongqing, 20 million people. You need to look at what's happening all around that city, what industries are there, where is the wastewater treatment plant, where do you put your electrolyzer, where do you capture CO2. There's another facility near us in Bantry Bay. It's a oil storage place. So we're looking again there at bringing in offshore wind and having a Haber-Bosch process and we're looking at 10 gigawatts of offshore wind to hydrogen, capturing nitrogen from the atmosphere and having ammonia. And there's already ammonia there. So we're looking at producing renewable ammonia, and that could be used for agriculture, but it's very suitable to be transported by ship out of Bantry. And I suppose what we have found is that Ireland is a relatively small country. We have a population of 6 million. We have a huge resource, and our European neighbors, we've had the Germans are coming to us, the Dutch are coming to us, and they want us to give them H so that they can continue making fertilizer and ammonia and methanol. So Rotterdam wants Ireland to supply either electricity or hydrogen or ammonia to a scale that would replace Russian natural gas. I do think that energy security has trumped climate change. I mean, there is a crisis in Europe. We don't have natural gas to the extent that we did. And how do we make ammonia? How do we make methanol? How do we make Mercedes? How do we make steel? And I think Ireland is seen as some country that can provide lots of energy to Europe.
Okay, thank you. Thank you for your answer. So any question from our audience? I can see there is a note. Someone just corrected us that he said Chongqing has more than 30 million people. It's more than 20 million. It's bigger than...
Yeah, I have a very good friend, Ao Sha, in Chongqing University. It's a lovely city. Is it 30 million people live in Chongqing?
Yes, I guess 30 is the right answer. Yes.
I hope I haven't done too much and confused the audience by doing too many things.
Okay, I just have one more question. So what do you think will be the major challenges if we want to distribute all these technologies?
In an Irish context, we do worry about planning. It takes a long time for communities to engage and to accept processes. So if we proposed producing hydrogen in Ireland, we'd be very worried about public perception and the ability to get authorization. And that is a reason why we looked at putting an electrolyzer on a wastewater treatment plant. You know, people don't go to wastewater treatment plants. So we do worry about public acceptability. You know, when you mention hydrogen, people think of the Heidelberg accident. We had a situation in the west of Ireland where we had a new gas field and people lay down on the beach to stop the pipe coming ashore, and they went to jail and they wrote ballads about them and they became heroes. So We worry about community engagement. We always believe the technology is there. Like we know how to make hydrogen. We know how to make ammonia. The oil industry would say these fuels are things we're very, very comfortable with. So technology is there. It's picking what is the right technology for this country, for this region. Do we want methanol? Do we want ammonia? Do we want hydrogen? Is it for buses? Is it for trucks? Is it for planes? How do we make most money? How do we bring the best value? How do we have jobs for our children in our community? So I think every city, every state will have different applications, and it's winning people over. So within our center, we do a lot of community engagement. We do a lot of co-design. We try to figure out what the valley wants. So we talk to fishermen, we talk to restaurants, we talk to industries. We try and bring them all together, and the byproduct from one industry could be of great asset value to another industry. So it's tying up distilleries, wastewater treatment plants, cement factories, having serendipitous connections so you can create cascading systems, but you need community involvement. And we do find that in a European context, well, in an Irish context, can take 4 or 5 years, and you have to persuade people that this is good for your community. And typically the people work in industry. So we talk to industry, we talk to the employees, we talk to communities, and it's getting acceptance. I think that's the biggest challenge for decarbonization. People want to decarbonize, but they don't necessarily want a wind turbine in their community. They don't necessarily want an ammonia factory down the road. So it's that co-design.
Okay, thank you so much for your wonderful presentation and your answers. I think now we just have very limited time, and let's just come to the end of this session. Thank you again, Professor. If I have further questions, I may just send you some emails.
Thank you very much, and thank you for the invite to present. It's my honor.
Okay, thank you. Okay, goodbye.
Bye.